Hi guys, I'm back. Well, I thought we'd continue on with looking at a little bit about inductors, and then we're going to look at resonance circuits, primarily IFs a little bit. And for those who commented on the last videos, thanks for your comments. I'm going to try to get back to some of you. There were some questions on there, so I can answer them pretty easily just by typing it in, so I don't need to make a video on that. So anyway, let's look at, we left off where I was going to start going into mutual inductance. So we're going to do that real quick and then look at inductors in series and in parallel, and then we'll move on to the IF transformers. So mutual inductance is M, just for mutual, equals. Now there's actually two different ways of doing this depending on how you look at it. We're looking at some sort of set of coils, transformers. They can be iron core or air core, it doesn't matter. But we'll call this L1 and L2. This one here will have a current through it. We'll call it I2. There'll be a current in this one. We'll call I1. And across here we have the MF. And across here EMF, okay, or voltage. Mutual inductance can equal the EMF induced in L1 divided by the rate of change of I2. Alright, that's one formula. All that's saying is if I'm putting an AC circuit or AC current into L2, it's going to induce a voltage, or EMF, in L1. The amount that it produces in there is in relation to the frequency or the rate of change of I2. So whatever that frequency is will be what the voltage is produced over here. The other formula is just reversed. It'll be the EMF induced in L2 divided by the rate of change of the current of I1. So the other formula is just saying that if I hook this up to some sort of AC signal, whatever that frequency or rate of change is of the current here will be the EMF over here. It'll divide into that. That'll be the mutual inductance. How well are these coupled? That's all mutual inductance means. It's not it basically is an experimental thing. There's an actually real theoretical formula for it that is a lot more complex than this, but if you just actually would take a transformer or a couple coils or whatever, you can actually just measure this and then work out your mutual inductance. Now that comes back to the coefficient of coupling, which is K, which equals the mutual inductance divided by the square root of L1 times L2. So basically all this formula states is the inductance of L1 times the inductance of L2, take the square root of it, divide it into the mutual inductance that you measured, will give you K, or coefficients of coupling. Now all this is only just for your information. It serves nothing unless you're going to be building transformers or the like. So, but I thought I'd throw it out to you. Now inductors in series, if I've got some inductors that are tied in a circuit in series, they're pretty easy to figure out to a certain extent. So if I've got like a circuit here with an inductor, and then another inductor, then another inductor, and I call this L1, L2, and L3, the total inductance, LT, equals L1 plus L2 plus L3. In general, as long as these is separated so that they're not having any mutual inductance amongst them, that's all you use. It's just like series resistance, same formula. Now if they were actually fairly close together, where I would have a circuit where I'd come along and take, say, one inductor here and then another inductor here, and they're pretty tight together, like around a band switch or something like that, instead of having like an inductor on one end and then a little ways away another inductor and then another inductor, where they're separated by a few inches. If they're pretty close together, then we'll call this L1 and L2. Then LT will depend on the mutual inductance. If the mutual inductance is additive, in other words, if these coils, these two inductors, are such that the current going through them builds a magnetic field in the same direction, so that basically going through the coils, the two coils are wound in the same direction and hooked up that way, then where the mutual inductance is additive, the total inductance is L1 plus L2 plus 2 times the mutual inductance. If one coil is reversed wound as compared to the other one, then it subtracts. LT will be L1 plus L2 minus 2M, or 2 times the mutual inductance. In some cases, in a lot of cases like this, this will come out with 0 inductance. When you add these two together, and the mutual inductance generally will be about high enough that 2 times it, the actual will subtract out, so that there is 0 inductance. Now, inductors in parallel is just like resistors in parallel. So if I've got call L1, L2, and L3, total inductance, L total, will equal 1 over 1 over L1 plus 1 over L2 plus 1 over L3. And mutual inductance doesn't matter in this formula. So it doesn't matter how close they are. Same as resistors. When you got resistors in parallel, it's 1 over the sum of the reciprocals of the resistors. Now, let's look at some IFs. So, I got an IF transformer, and it's probably air core, at least this one will be. And let's say it's got our tank circuits, our capacitors. Now they could have a core in there where they're adjusted and these adjustable, and the capacitors are fixed, or they could be like an older radio where the capacitors are adjustable and the coils are fixed. We'll just make the caps adjustable. This is our primary and our secondary. When I feed a signal in, you know, this would be hooked to the mixture tube, converter tube, say, and this side is going to my IF amplifier tube, like a 6SK7 or something of that nature. When I feed a signal in, this part of the circuit is a resonant tank, and it will act as a parallel tank circuit. What it'll do, though, as the signal comes in here, a magnetic field will build, which will cut across this winding here. We'll end up with a coefficient of coupling here, a mutual induction. So this thing induces a voltage into this coil, which then will feed it out. The thing is, on this side, on the primary side, is a standard tank or parallel circuit. This side is a series circuit. And the reason for that is the way the signal's being applied. Over here, I'm applying the signal. I'm just going to use something like this. That's just basically a symbol showing an AC signal. I'm applying it parallel. So it's being applied both to the capacitor. The voltage is the same both on the capacitor and the inductor. So they're in parallel as far as voltage is concerned. But this circuit here is getting its voltage from the mutual inductance from this. So it's as though I'm applying the signal right to the coil. So you can think of it as really more like a series circuit, where this gets applied in here, the voltage builds on the coil and then feeds out through the capacitor and acts as a series circuit. So this can be redrawn more or less like a coil with a capacitor, and then this will feed out to my load. We'll just say load, and that feeds to our load. Since I'm not applying the signal this way, it's applied inside the coil here. So the voltage builds up here and then feeds out to the load. Otherwise, they're basically the same. As far as figuring out what the resonant frequency is, it's the same formula. They both use F equals 1 over 2 pi square root of LC. They both use the same formula. The only difference will be the actual impedance will be different. This circuit here is actually a fairly low impedance circuit relative to this circuit. This one responds more and will work out better and turn out to be a higher impedance circuit feeding in to whatever the load is, whereas this one is actually a lower impedance circuit. But that's the only difference between them. As far as resonant frequency, they're exactly the same. So if you was actually going to design one, you basically would use you could use the same size inductor capacitor to make up that IF transformer. And you generally see that. Most IF transformers are 1-to-1 transformer. You don't really ever measure the true impedance. You measure DC resistance, but generally they have the same number of windings using the same size wire, so the resistance, the DC resistance, will be pretty darn close, exactly the same. They use the same size caps, whether they're trimmer caps. These may be trimmers, such as the older IFs, or they may be fixed, but they'll be the same size. So the biggest thing just to understand about it is how it actually works is the fact that I feed the signal to both legs here, but it's induced just in the coil and feeds out. The capacitor appears to the circuit as being in series with the coil, so it becomes a series resonant. And it didn't happen as accident. We want this to be a little bit higher impedance to match, to work out and match out to the grid circuit, because this is going to tie to the grid of the IF amplifier tube. Grid circuits are high impedance. We like to keep those matched, so that way the signal feeds in just fine. So there's not a whole lot else to say about these. They're really a simple thing. One thing to remember about them is if you're actually wanting to look at from the standpoint of phasing, as this one goes up, this one goes down, and this one goes negative, this will go positive. But it's not really that big of a deal. It doesn't matter. But they do shift in phase because what is being produced here is counter EMF. It's counter to the voltage here. So that's about all I've got to say on them parts. And inductors for all practical purposes. I might go ahead and give you one other little thing here. You've got a transformer, audio transformer, but it can be any number of other transformers. But let's just say an audio transformer. You got the primary here, secondary here. This side goes off to generally B+. This side goes to the plate of the output tube. And of course, you know, the secondary goes right across the voice coil. When you look up a audio tube, one thing that in a tube manual, it's going to tell you what kind of impedance load that tube looks for. It could be, 6,000 ohms, 8,000 ohms, 10,000 ohms, something like that. But yet, if you measure the average audio transformer you find on radio, if you measure this, it's going to be around a DC resistance around like 400 ohms or 450 or somewhere in there. There may be some as high as 600. Some a little bit less than 400. But it's going to be somewhere around in that area. long far cry from a few thousand ohms. Well, how's that work? Well, it's a little thing called reflective impedance. This goes out and hooks into my voice coil. I'll just say VC, and that has a certain amount of ohmage to it. In general, on most of all these old radios, unless it's absolutely given, and if it is, it's going to be like 3.2 or something like that, 3.1, 3.5. There are some out there, certain ones that were down under 3, but you can generally figure just 4 ohms and that'll work just fine. Because modern day speakers, voice coils, generally are 4 ohms or higher. But if you figure 4 ohms here on the voice coil, that reflects through and creates an impedance here on the secondary. The 2C, this one will see the same thing as 4 ohms here. That actually reflects back through the transformer back to the primary. Now, an audio transformer basically is a step down voltage transformer. If you think from voltage standpoint, it steps down, meaning I have a high voltage here, high number of windings, and that steps down that voltage to, because I have quite a few less windings here. So whatever voltage is here, I'll have a lot less in comparison to what that turn ratio is. Now it steps up the current, and that's only reason why they do that is, for one reason, is because current is what actually does work. That's what you really need in that voice coil to get it to move and to do its job. The impedance will follow that turns ratio. So going back this way, we're stepping up, so it steps up the impedance. Now there's a nice little formula for that, and that basically is, we call this the primary and secondary. So the number of turns on the primary divided by the number of turns on the secondary, so your turns ratio will equal the square root of the impedance on the primary divided by the impedance on the secondary. Now you can flip-flop it, you can just square both sides, so you'd have the number, your turns ratio squared. So the number of turns on the primary divided by the number of turns on the secondary, both of them squared, will equal just the impedance ratio, primary to secondary. So if you really was wanting to try to find a transformer and you only knew the turns ratio, or you was trying to figure out, or ordering by turns ratio or whatever, you could take what you know, I need 4 ohms, I know what I need here, and you could actually work it out to get this by just using this formula. But that's all it is. It just basically follows the formula, just same as everything else follows in here. Remember, impedance is just AC resistance, so it's just measured in ohms. So it follows Ohm's law. So basically the EMF, or the voltage, the signal voltage, equals the current, the signal current, times the impedance. So that's why it follows this turns ratio, is because the voltage and current both follow that turns ratio. And there's nothing really magical here. That's just basically all it is. The few things that you really need to know if you was actually designing something, or if you had to replace a transformer, the few things you really need to know is a good idea, or general amount of impedance that's on the voice coil is, you know, like a 4 ohm speaker or whatever, and the tube you got, what it's looking for the impedance in its plate circuit for load, and that's in the tube manual. So once you know those two things, then you can figure out what you need for a turns ratio transformer. And the unique thing about this, you really don't almost need this unless you was winding your own transformer, because if you look up replacement transformers, they give you this information. They actually give you this formula. Most places do. But they give you this information. They tell you, well, if you're going to use, you know, a lot of them are universal, so they'll be like 4, 8, 16, whatever ohms on the secondary, but they'll tell you if it's at 4 ohms, you'll get, you know, so many thousand ohms on the primary. But that's how it works. There's not a whole lot more to say on that. Really. I might, well, I guess that's about all I've got on this. I think on the next video we'll go into just straight AC. We'll talk about impedances. We'll talk about basic filters, low pass, high pass, things of this nature that you'll run into and deal with in circuits. Anyway, I don't really have much else to say. For the future, now this is down the road. I'm not sure exactly when, because it depends on when both I have the time and I can get the funds available. But I thought I would go ahead and do an actual from scratch design and work up a design and build a audio amplifier. Just audio amplifier. I kind of actually done that already. If you go back on my videos where I did a signal tracer, that's nothing more than just an audio amplifier. But if I got the parts or can get the parts and stuff, we'll do a push-pull audio amplifier and stuff, and we'll just do a design from scratch, and it'll be a kind of a lengthy series going through the stuff that you got to figure out and everything, going from scratch and building one up. And also I'll go through where I find the parts and all that stuff. So look forward to that. It's probably a few months anyway down the road. So I really can't think of anything else. If you have any questions, just leave them in the comments. I might go ahead and answer at least one of the comment questions. There was a question, or they were just kind of, it wasn't actually a full, really, you know, just kind of wondering why something happened. And that, you know, that goes back to the amplifier. And I was showing in the last video, hey, come on, focus. I was talking about these 200Ks on both the tubes, the left and right, both of them being open, and just curious about why they would be. The primary thing is the reason is just too much current through them. It opened them and opened them quickly. They're the plate load, and if that tube starts drawing way too much current, now if it's just a little above what should be, they would slowly burn out. But if it would spike real quick or go way high, if this tube went in full saturation, it could take out them resistors without actually burning them out. It would just take them out internally. So my guess is, if I was to reckon a guess, the coupling caps to the grids on both these probably went extremely leaky or even dead shorted. The possibility also exists that the coupling going to the output tubes also were leaky and helped along with this. But that's the reason why they went out. It was more like signal current than actually DC current. But and if it got a spike on that signal and push this tube in full saturation, a huge amount of current going through. I'm going to talk a little more about this when we go over this thing. That's coming up in a future video, going over the restoration of this RCA amplifier, because this is an interesting tube circuit. This tube doesn't hook like most tubes do. The cathode doesn't, because if you notice that the cathode is tied off through a resistor and comes back around to the output of the audio output transformer. So there's a reason for that, and we'll talk about that when I start doing something on that. But that's what took them out. It's nothing really, just the leaky caps. And so anyway, that's kind of the answer to that. The other question that I had on here, let me bring them up, has to do with some other stuff. And I was going to type it in, but I think I'll just go ahead and answer the question. I might go ahead and type it in anyway. Let's see if I can find it. Oh yeah, here we go. One of my commenters on here wanted to know if I could do a video on rebuilding a couplet. Oh, by the way, they're couplets, not couplets. A lot of people call them couplets, but the actual true name is couplets. And in fact, interesting enough, I believe, yeah. Let's see here if I can find it on the camera. There we go. That's what we're talking about. What's in this dotted line right here is a couplet. And this is actually a little bit different. It's still acting as that, but it's also really the filter. This is the circuit for your treble and bass filtering circuit, and also couples the circuits together. But anyway, want to know about can I do a video on rebuilding a 4-pin? And my best answer is that yeah, I could do a video on it, or at least something kind of talking about it, but there's been videos already done, not by me. So I'm gonna actually would send you over to someone else's channel, B. Anderson TV. Look him up. Look up his channel. If you have any troubles for whatever reasons, I know YouTube's kind of funny when you do searches on there for, especially YouTube, people on YouTube. You can just go to my page, my channel, and look up. I'm subscribed to him, so you can look up in my subscription to find him. But in any case, go to his channel. He's done several videos on rebuilding these things. Various different ones, various different types, various different pin outs, and everything. Mainly in the predicted TVs. He done quite a few extensive videos, and so go to his channel, type in the search Predicta. That's all you got to do, and it'll take you, because he's got he's done several series on several different predicted TVs, and in several of them he's shown how he came up with different means of rebuilding those couplets. And so they call them K networks, and Philco did. But so check out his channel. I think you'll find what you need there. Watching, there are several videos, and I think you'll find it interesting. He goes over the parts he uses and everything. So check it out, and I think you'll find the answers to that. As far as the rest of the comments on the last video was just basically everybody enjoying the video. So thanks again for that, guys. So anyway, if you're new to my channel and you, I also do videos, and I will be starting another little series on an RCA amplifier. I got to finish up on a RCA Redola radio, which I'll also be doing another video on. So I do videos on restoration of radios, but also do stuff on theory and on you know, like reading schematics, tube theory, and everything else. I got several videos already up. So if you ran across my channel, you like any videos, anything dealing with tubes, just subscribe. If you like this video, please give it a big thumbs up. And I guess I'll see you guys on the next video. So thanks again for watching.